Good morning, everyone. My name is Sharmika Epps-Harris, and I am the new Director of Annual Giving and Donor Relations at VCU Massey Cancer Center. And I would like to thank you all for joining us today for the virtual Massey Club Innovators Forum. This year is a special year as we celebrate the 30th anniversary of Massey Club and the impact that donors have and continue to make to Massey through unrestricted support. While we had hoped the fall edition of this event could be in person, we are excited to showcase two dynamic researchers during today's program. Before we begin, we pause to acknowledge the passing of Massey Cancer Center's founding director, Dr. Walter Lawrence Jr. In his passing, it is difficult to articulate the profound impact that Dr. Lawrence had on the lives of countless patients, students, and colleagues, and the landscape of cancer research and care. This short video will highlight his quest for social justice and health equity, advocating tirelessly to improve health outcomes for all.
Our medical school, we're saddened to hear the passing of Dr. Walter Lawrence, truly a giant, not just in our community, but a global figure in medicine.
Walter Lawrence not only founded Massey Cancer Center, he was a consummate clinician scientist, medical educator, and a phenomenal clinician.
I keep reminding people that it was Dr. Lawrence who actually fought for the admissions of LaSalle Lafall, who was one of the greatest African-American surgeons from Howard.
Dr. Lafall was nominated for membership in the Southern Surgical Association. Unfortunately, due to prevailing thoughts around race, Dr. Lafall's application was not approved. Dr. Walter Lawrence at that time said, if Dr. LaSalle Lafall is not good enough for the Southern Surgical Association, neither am I, and he resigned from the Southern Surgical.
In a city that for a long, long time was a capital of slavery and later racism and Jim Crow and white supremacy, this was a man of principles and integrity.
People who were forward-thinking like him frequently did suffer repercussions for that. I have no idea why he was so adamant about his views on civil rights and about doing the right thing. I can only be grateful that he was.
I was the only African-American woman in my class. I think he realized Black students needed someone that they could confide in.
His ideals of making cancer care available to all people is something that is underscored by VCU and Massey's commitment, and it is something that he ended up starting from the 1960s onwards.
And he served as a mentor and an inspiration to me for more than 4 decades. He was like a second father to me. He will be sorely missed by all of us who knew him.
Dr. Lawrence was a font of eternal optimism. It was an important lesson to know that sometimes the best medicine that you can offer a patient is your own positive personality and sense of optimism.
His intelligence was tremendous, but his emotional intelligence was really the hallmark of him, and I think that's what allowed him to bring together a group of people.
For me to be here and to be in the presence of Dr. Lawrence has been a total full-out blessing for me, and I really believe I've been the luckiest cancer center director in the world.
All I can say is he was a spectacular person who I am so proud to say that I was taught by him.
His legacy today can be felt throughout this institution, and that perhaps of all he achieved in his life will be his greatest gift to all of us, that we, as best we can be worthy to be colleagues and inheritors of the character and the integrity and the excellence of Dr. Walter Lawrence.
We not only acknowledge, but celebrate Dr. Lawrence's life, his accomplishments, and the legacy that he leaves right here at Massey Cancer Center. As Massey Club members, each of you help support the mission of Massey and help fund innovative projects and research that may otherwise be left on the drawing board. To thank you for your support, we have a message from Adrian Maxwell, a Massey Advisory Board member and founding member of Massey Club.
I would like to thank all of you Massey Club members for being members of the Massey Club, because it is a very important club. My late husband used to say it was the best club he belonged to. The Massey Club was started because it is unrestricted funds that are under the directors of the center's discretion. Often during the year, something comes up that could be very crucial for a project. It could be hiring someone, it could be a piece or something like a piece of equipment or a recruitment project. If he doesn't have unrestricted funds, his hands are tied and he has to wait until the next year in hopes of getting those funds and may miss out on an opportunity. So the benefit of the funds in the Massey Club is that the funds are unrestricted and have been very important in the growth of Massey Cancer Center and what it has accomplished. As you know, that when we started the first year, Massey Club had 37 members and now is over 500 members. This has made it possible for not only our growth, but our success in many of the honors that we have won in awards from our projects. You have really invested in people, invested in our scientists, and the benefit has been to the people who have profited from some of the research that we have done. So we feel the Massey Club has helped fulfill our goal of helping people live longer and better. So we want to thank you for investing in people. Thank you.
I thank Adrian for that message. I know she's joining us today virtually. So thank you, Adrian, for being an advocate for Massey Club as well. As we launch today's exciting conversation, I kindly ask that all attendees please mute yourselves during the program. It is now my pleasure to turn this event over to my colleague, Cindy Bade, who will be moderating today's conversation. Cindy, the floor is yours.
Thank you, Sharmika. And I want to thank all of our Massey Club members and Massey donors who are joining us today. We are so grateful for your support and what you help us do here. As Sharmika mentioned, my name is Cindy Bade, and I am a major gift officer at the Massey Development Office. And today we are going to be talking about metastatic cancer, what it is, why it happens, some of the challenges in treating it, and how our researchers here at VCU Massey are working on ways to solve that problem. Our panelists today are innovators and leaders in their field, and we are so fortunate that they are part of our team here at Massey. So it is my pleasure to welcome Dr. Paul Fisher and Dr. Andrew Poklepovik. It's great to have you both here today, and we thank you for taking time out of your very busy schedules to join us. I'm going to ask each of you to introduce yourselves and just tell us very briefly about your role here at VCU Massey and what you do, starting with Dr. Fisher.
Well, good morning, everybody. I'm glad I had the opportunity to do this. I am professor and chair of the Department of Human and Molecular Genetics, founding director of the VCU Institute of Molecular Medicine, and hold a chair in the Massey Cancer Center, the Thelma Newmeyer Corman chair. Our work focuses on trying to understand the process of metastasis, which is extremely complex, and using that information to help develop molecules and approaches that can be used to treat this devastating disease, which causes morbidity in more than 90% of advanced cancers. So I'm going to turn it over to you, Andrew.
Great. Thank you. I'm really excited for the opportunity to speak with you all today. So I'm Andrew Poklepovik. I'm a medical oncologist. I've been with the Cancer Center since 2008. I am a solid tumor medical oncologist with a focus on melanoma and sarcoma, but I also help to run our early phase clinical trials program, which tests new treatments that either come from the lab or from other investigators. I'm the medical director of the Clinical Trials Office as we embark on a massive growth and expansion of our clinical trial portfolio. I'm also assisting in the Molecules to Medicine initiative, which collaborates with investigators like Dr. Fisher to bring new molecules that have never been previously tested in human patients with cancer, but show great promise to the forefront so that we can develop the next level of treatments for these patients.
Well, thank you again for both of you, for being here. I'm going to start off by asking you, Dr. Poklepovik, tell us about cancer metastasis. What is it? Why does it happen? And what are some of the challenges in treating it?
So metastasis is what we think of when we talk about someone's cancer being stage 4, where it is spread throughout the body. It is no longer considered operable in most cases. And the way to think about it is as tumors form and as they evolve and gain increased deregulation of normal processes, they develop the ability to leave where they started, survive in circulation, land somewhere else, and then develop a new colony of tumors. And the cancer cells have to go through a variety of complicated pathways in order to exit their primary tumor, get into lymphatic channels or the bloodstream, survive the time in circulation, then set up shop in the new tissues to create a new tumor and a new site of disease. These are the types of cancers that we have not had success in curing historically. We can do surgery on cancers that haven't yet spread. We can do chemotherapy in patients that might have microscopic levels of spread. But once it has been spread throughout the body in a way that we can see it on imaging and scans, traditional chemotherapeutics have been unsuccessful for long-term disease control. In a subset of patients, we can leverage the immune system and gain control over cancer and metastasis via immune-based therapies, getting the immune system to recognize the cancer. But that only works for a minority of patients. And understanding the process and how does a cancer cell start in one tumor, migrate to another place, and then set up as a new lesion, understanding that process and disrupting that can go a long way to reducing the burden of cancer in patients.
And can you tell, as a follow-up to that, can you tell us what is the kind of outcome prognosis between, say, a patient with a localized stage 1 cancer and a metastasized cancer?
So as we think about it, just to use a cancer that I treat as melanoma. So a localized melanoma that does not have metastasis, say a stage 1, carries a long-term survival rate of 96%. An advanced melanoma of stage 4, if not treated, carries an average survival of 6 months. And this holds true across cancers. Patients with stage 1 and stage 2 colon cancer are highly likely to become cured and survive. Most patients with stage 3 colon cancer will survive, but the survival of patients with stage 4 colon cancer is on the order of about 2 years. Maybe 2.5 years with modern therapy, with some patients living longer. And that holds true for most cancers. Pancreatic cancer is curable in early stage, incurable in late stage with an average survival of less than a year. So understanding this process and this phenomenon can go a long way to altering the time course for someone's expected survival.
Absolutely. Well, that is a perfect segue to my question for Dr. Fisher. So your lab, which I should say includes you and an entire team of other brilliant scientists, you really focus on understanding why cancer cells behave the way they do, and then use that knowledge to try to develop new therapies and treatments to combat them. So I understand that your team has been working with a new molecule that you feel has some promise to fight cancer metastasis. So can you tell us about, first of all, how do you discover a new molecule? And this particular molecule you're working with, how does it work?
Okay, so I'm going to go back to my youth, which I hate that term, but when before coming to VCU School of Medicine, I was at Columbia University College of Physicians and Surgeons in New York. And our focus was developing techniques that would allow you to look at all of the changes that a cancer cell makes and how it's different than a normal cell. And what we did is we developed an approach which became a standard, which was to subtract away everything that was being made by a cancer by its normal counterpart. And we identified genes that were key regulators of this devastating process. As Andrew indicated, one of the major components of metastasis is it occurs in different stages. You know, this cancer cell has to invade, it has to survive, it's got to now attach at a different site, it then has to regrow, the immune environment is changed so it no longer recognizes the cancer. So using these approaches, we identified in melanoma, a gene called melanoma differentiation associated gene 9. And what I've learned very early in my career was anything I name, someone's going to name something else, because they become standards of genes that are located in what's called the whole genomic database. So all of the genes that are out there. And we had this gene, and we knew that this gene was involved in 8 of the 10 steps in metastasis. And I'd like to emphasize that one of the reasons we believe you cannot treat metastasis effectively is that the therapies target 1 or 2 of these stages. And a cancer cell continues to evolve. So if your cancer has now got cells at one stage versus another, and you're targeting only one stage, you can avoid treating the bulk of the tumor, cells survive, and then you get micrometastasis, as indicated by Andrew. Long story short, we worked with chemists in the Sanford Burnham Cancer Research Center in La Jolla, California, and they had developed a technique for actually identifying molecules that could bind to our protein. And we identified a molecule that actually was able to bind to this protein and prevent it from exerting its effects. This is a small molecule that we're now working on extensively. If you go into the genomic database and look at all of the cancers, this gene is upregulated in almost all different cancers. So it's not only melanoma, it's breast, it's prostate, it's glioblastoma, which is a very devastating brain disease, and many others. So we've identified this gene, we've identified the molecule, and we're now at this stage. And I can turn it back to you, Cindy, so I can lead into something else. But I hope that was clear, and I'd gladly answer any questions later on.
Yes, absolutely. So basically, this molecule turns off a mechanism in the cancer cell that allows it to keep propagating itself.
That's exactly it. It stops it basically in its tracks. Now, it doesn't kill the cancer. So what happens when you combine this with standard of care therapies that are being used by Dr. Poklepovik, it makes them work better. And we've actually now figured out how it makes them better. It allows them to accumulate more of the toxic molecule so that it effectively can kill the cancer. And this allows you to use lower doses, which will be critical in clinical trials, so you don't have the toxic side effects.
Fantastic. So how do you test a molecule like this? Obviously, we're not in human clinical trials, so tell us about that process of testing a molecule in the lab.
Okay, so the first way you test it is by growing cells in culture. And you can grow human tumors, you can grow tumors that develop in animals, and then you look at their biology, you look at their response, you look at toxicity, you compare that. Does it hurt a normal cell versus the cancer? Does it have any selectivity? And once you've gotten to that stage, the next stage is critical, where you test it in an animal model. And there are two types of animal models that are used. There are animal models in which they do not have a full immune system, which allows you to grow human cancers. So you can actually take a cancer from a patient, called a patient-derived tumor, and you can grow this in the animal. The other ones are ones that have an intact immune system. So they more mimic what a person would have. And these cells can now grow in that tumor, and you can test them to look at the effects on the immune system and the cancer directly. So once you've done that, and if it's worked, you're ready for the next phases.
Fantastic. So what stage are you at right now? How many phases of the initial research have you gotten through, and kind of what is your next step?
Okay, so we've gone through all of the initial phases. We've tested this in cells and culture. We've tested this now in animals, and it works. And based on the science in the beginning, we knew that it blocked many of the steps of metastasis. So it blocks the ability, for example, for a tumor cell to now locate and colonize in the lung to give you lung cancer. So we know it stops it from attaching. We know it blocks an essential component, which is the blood supply. In order for a tumor to survive, it needs a process called angiogenesis. It needs to set up new vessels so that it can supply its nutrients and continue to grow. We show it blocks that. And we show the ultimate effect. It blocks the tumor's growth and metastasis, and the animals survive better. And when you combine this with the second agent, we're getting some really pretty spectacular results now in a number of different cancers. So we're very excited at the stage we are now.
Yeah, that is fantastic. Very exciting. Dr. Poklepovik, as a physician who treats patients who present with metastatic cancer, what does having a new therapy like this mean to you and mean to the patients and the families that you serve?
New therapies are critical. The advances that we made in cancer over the last 10 years, with some of the greatest gains in survivability, have all been due to new treatments. But by no means is that all of the cancers that we face and all of the treatments that we need. We need so many more things. And finding the areas where there are big gaps, the approach to the metastatic potential of cancer cells, preventing it from spreading to other locations, limiting that process, can open up many doors. In addition, Dr. Fisher's work actually shows that it strongly enhances the effect of other traditional agents. So, improving the outcomes for cancer is of critical importance, and to identify a brand new process and pathway to explore and leverage is critical and potentially groundbreaking for patient care.
Yeah, absolutely. And how exactly, tell us how you and Dr. Fisher partner to really take a new therapy like this from the lab into the clinic, and how do you overlap and collaborate on that?
So I speak, as I refer to it, labese, where there's a laboratory dialogue with deep understanding of biology, biochemistry, mechanisms, pathways. And I don't understand it anywhere near to the level of Dr. Fisher. I'm not fluent, but I understand and can have working conversations about where that is. What I do speak is the clinical need, the development and design of clinical trials, the areas of cancer where some of the largest gaps are, where if we can place an effective treatment, it will have an immediate and strong impact. And by doing that, we have conversations, and then sometimes the experiments are refined to bolster the evidence to support, hey, we should be looking at this in liver cancer. We should be looking at this in pancreatic cancer, knowing the problems that we face in those particular cancers and how this might overcome that. So it's really a back and forth. And then ultimately, as these concepts do get brought forward, the things that we learn from clinical trials go back to the lab to talk about the refinement and further understanding. And so we often hear about bench, or the laboratory bench to the bedside next to the patient. And really what we are actually doing longitudinally is bench to bedside to bench. And it's always going back and forth with that dynamic to really build upon what we know, ask new questions, and learn more.
Yeah, absolutely. Fantastic. Dr. Fisher, I'll turn this back to you. So we've all heard in the media and just general knowledge about how long the process is to get a new drug to market, to get FDA approval and actually get it into patients. Can you kind of walk us through that path and what it takes in terms of time and resources?
Okay, and I think Andrew, Dr. Poklepovik is being very humble. He's a major component, and it's really the give and take that allows us. So we know after speaking to Andrew what molecules may not be working well or could fill a gap that's needed. And we try to go back and forth. And if agent X is now being used that's showing some efficacy, we can test it to see if we get improved efficacy. It is a long and arduous journey from bench to bedside and back to bench. I have to emphasize that. The critical stages are to have enough information to then have a dialogue with the FDA, and you submit what is called a pre-IND. So an IND is an investigator new drug application. And the pre-IND is very important that you get feedback as to what they think you're doing right. They'll never tell you you're doing something wrong. They'll just say, this has to be changed. And then you go back and then you modify this and you perform what is needed. And the critical facet of this is that toxicology becomes a really, really important issue. You don't want to put anything into a person that could make the situation worse. And this is a long journey because there are special protocols that have been set up, special models that you have to look at that are done externally by companies, which is really quite expensive. You can't do a lot of this in-house. And then once those are done and you get a clean bill of health that the approach is not toxic, it looks like it could work, you come back, you sit down with Dr. Poklepovik, and you now develop an IND, which is you're ready to go and then approach the FDA to get approval to then set up a clinical trial. As you can see, this is a long journey. It just doesn't happen instantaneously. So it's a combination of the science, the medicine, the bureaucratic system that we have to deal with, and then finally the outcome, which is to have a phase 1 clinical trial in patients. Andrew and I are hoping to go forward with this, and we're at a stage where we're ready to do final formulation that we think will work in people. This will be tested for toxicology, and then we're ready to move full steam ahead.
Fantastic. And when you do a clinical trial, is that just here at VCU, or will you find peer institutions that will also participate in the clinical trial?
Okay, I'm going to start that, and then Andrew can pick up. We've always looked at multiple institutions. I had identified a cytokine called IL-24, a different molecule that can be used therapeutically. It was developed at Columbia when I was there. It went into a company. The company licensed it to another pharmaceutical company that actually did the test at MD Anderson. And then there were 3 other institutions that were involved. And I think with the studies we're doing, we would like to, and I'll let Andrew amplify on that, look at it depending on the clinical indications, potentially at VCU as well as other institutions, to get the number of patients samples that are needed, number of trials set up effectively. Dr. Poklepovik, so I'll turn it to you.
Sure. We do run multi-institutional clinical trials, including those that we have translated. And when I say translated, I mean take the scientific experiments that come out of the lab and turn that into a clinical trial protocol that patients are able to be treated on. One translated clinical trial is a a breast cancer preoperative, otherwise known as neoadjuvant clinical trial, leveraging gene expression modifying treatments along with immune therapy in the hopes that we trigger greater responses to standard treatments for women with locally and regionally advanced breast cancers. That clinical trial is run by us. It's Massey Science. Ohio State has it, St. Elizabeth has it, University of Virginia has it, and we're the coordinating center. And so that's the type of collaborative care that we establish with other institutions as these trials get off the ground to improve the timelines for completion of accrual, because 4 centers all looking for patients is going to, get 35 patients faster than 1 center looking for patients. And so we also have networks that we have, we're all in this together. And every oncologist and laboratory scientist has one mission, which is to cure cancer and ease the burden of the disease and of the treatments. And so it's a very collaborative group. And so having those opportunities and those connections enables that to happen. And Dr. Fisher is very well known in the scientific community with lots of connections that I'm looking forward to leveraging one day to have a multi-center trial with his molecules.
Absolutely. And just building upon that, can you talk to us, Dr. Pok, a little bit about more about clinical trials and how they benefit patients and why patients should really consider participating in clinical trials?
Yeah, clinical trials are always recommended for patient care. And when people don't think, well, why would I want to be in a clinical trial if we don't know? Then the follow-up question to that is the treatment of cancer better today than it was 10 years ago? Our patients, do we have better treatments? Do we have more treatments? Do we have better survival outcomes and expectations for most patients? And the answer is yes. And those standard treatments of today are the clinical trials of 5 years ago. And so a clinical trial is actually an opportunity to gain access to a treatment for cancer that you could not gain access to otherwise. And it may be one that takes a standard treatment and reduces the toxicity, and maybe another one that adds a new treatment to a standard to try to make it work better. But it's an opportunity. And for patients with advanced cancers, I have a philosophy that we go through at the outset where we talk about why do you think clinical trials and why do you think about it at any opportunity that you can. We don't know what treatment is going to work for an individual patient's cancer. We may know that a treatment will work 75% of the time, but 1 out of those 4 people it will not work for. 1 out of those 4 people it may work beautifully well for. We don't know. And so the goal in terms of let's survive as long as possible, let's open as many opportunities as possible, is to really focus on exposing the cancer in a dedicated strategy to as many promising types of treatments possible. Because treatment 1 may not work, but treatment 2 may be fantastic. Treatment 1 and 2 may not work, but 3 is great, and you don't know. And so if you can sequence clinical trials intermixed with standard of care treatments as part of a bridge, you can expose yourself to so many more different types of treatments and improve the odds that one of the ones that's going to hit the Achilles heel for your cancer is going to work and add more time. And the more time you have, the more new drugs are available, the more opportunities become available, and you have an additional opportunity to try more treatments and extend things further. And I tell people it's a marathon, somebody with advanced cancer that we don't have a cure for at this time. But I've had patients that we were able to sequence enough treatments together and a new treatment came available that controlled their cancer for years on end. I've had patients where immunotherapies that didn't exist when they were first diagnosed became available during their treatment, and now they're in remission. Things that didn't exist in the beginning. So every opportunity to expose the cancer to as many promising, scientifically promising treatments is critical as part of the strategy.
Absolutely. Yeah, and I feel like having, been at Massey myself for just a couple of years, I feel that we are in such an exciting era right now where the discoveries are just really snowballing, and we're really deepening our understanding of cancer and how to better combat that. And I'm going to turn back to you, Dr. Fisher. Obviously, we are here today to say thank you to all of our Massey Club donors. Can you tell us a little bit about how philanthropy helps drive the work that you do in your lab?
Okay, well, thank you. I want to let you know so that there are conventional classic ways in which research is funded. The ultimate classic way is a government grant, which can either be an NIH grant or it can be a DoD grant or another grant that's out there. If you apply for one of these, it can take 6 months before you get even an indication whether a study section, which can be very arbitrary, either liked it or not. Very rarely does a grant get funded that first time. It happens, but it's maybe 1%, 2% of all the grants submitted, so it's very low. And then you have to go back, modify, put it in again. So you're now talking about a year and a half, maybe, before, if you're successful, to have money to work on that project. Another way one can fund research is through a company interaction. You know, I've been fortunate that I've started a number of companies. One of them did really well, actually was traded on NASDAQ and then acquired by GlaxoSmithKline. That was the holy grail of inventions and bringing them forward. They funded a large amount of our research that led to the discovery of one of our genes that is going into people, hopefully in 22, that will save lives. And the other component, which I don't want to underestimate, which I think is the major one, is philanthropy. I've been fortunate to be funded by a foundation called the National Foundation for Cancer Research, where they give you money for ideas and allow you to follow them. But the best money and one of the real inducements to come to Massey was the opportunity to explore the options, build on our ideas, and then bring them to fruition much quicker. And I am indebted to all of you and the Lacey family for all of their support of me coming here. I mean, it was a move from the big city to Virginia. New York is slightly bigger and it's got its share of issues, but this has been a real good transition, and philanthropy has been a critical component that it's allowed us to succeed and take us to where we are. And I am very grateful for all of your support.
Thank you. And Dr. Poklepovik, anything you want to add in terms of philanthropy and how it impacts your work?
The clinical trials that I've been running for the past 10 years have been funded by the philanthropy of the community of our area in our region. The trials that we've done, the patients that we've helped, it wouldn't have happened without it. So everything that I do is based upon that. And the trials that we've done and the publications that we've made and the talks I've given in the past are directly thanks to the philanthropy. We have pilot project funding. We have full clinical trial concept funding. We have laboratory experiment funding. We have the tools to leverage our ideas to the point that they can make an impact thanks to the community of support that we have. So it's 100%.
Well, thank you for that. And thank you again to all of our supporters and donors who are here today. I hope you can hear the passion and excitement from our two panelists, and truly your annual gifts make a big difference because they do help provide gap funding and pilot project funding for all of this work that we do at Massey. And those things can lead, hopefully, to better treatments, better outcomes for our patients, and potentially a cure. So thank you, Dr. Fisher and Dr. Poklepovik, for being with us. And now we will open it up to any questions from the audience. You can either come off of mute or you can type something in the chat box, but feel free to ask our esteemed researchers any questions that you would like.
I do have a question for Dr. Pak or Dr. Fisher. I know there's a lot of projects you guys are working on, but truly, like, what excites you the most? Really the biggest thing and the thing that gets you most excited each day moving forward?
Andrew, should I start? I can.
Just go for it.
Okay, so for me, it's the excitement of actually having something you've worked on in a lab. It's like one of your children progress all the way to a point where it can now go into the clinic and actually help theoretically to save lives. So this is the joy, this is the passion I feel. This is why they can reach me up till 2 o'clock in the morning. This is a genetic defect. I only sleep 4 hours. So the rest of that is spent really focused. And I think the person that accepts this the most is my wife, who's got extreme understanding of someone who works the way I do. But that's really the passion, to really see this translate and hopefully save lives. And working with Andrew is really a joy in helping to bring this, we hope, forward.
I recently took a blood test that's done by a company called Grail on a test called Gallery that's allegedly, or at least they say, pre-screens for 50 different cancers and gets them in the microscopic stage. Are we working with any of that at Massey? And what do you all think about that? I mean, I'm willing to try anything just to avoid cancer or at least catch it early. But I know, particularly talking with Andrew about pancreatic cancer, which my family has a history, early diagnosis is critical to that. And then I mentioned it to my gastroenterologist when I was having my fun colonoscopy. And he said there are also other blood tests out there. What can you tell us about what's going on with those sort of things, and how does that sort of translate to what we're doing at Massey? Are we working with that? And just a little insight on any of that, if you have any.
Sure, I'll take this one. Some of the most exciting developments in cancer are coming from the non-invasive, meaning simple blood test monitoring of cancer. And yes, I do have interactions with Grail and the Gallery. I have experience with Grail and the Gallery. I have a proposal with them for screening high-risk populations with unprovoked blood clots. Should be going up for review next month with the company. I have a meeting this afternoon with the company for Massey's participation in a very large, greater than 10,000 cancer screening, including underserved populations, for participation in a very large-scale trial with them. So how does that test work? It's very interesting. And why can it pick up so many different cancers? Well, as you age, you experience changes in your body, right? Your skin gets thinner, your hair gets gray, your joints hurt more. There's a variety of aging things that sort of say, I know, I can tell that I am older than I was 15 years ago. I feel it, right? Well, that's normal aging. And a lot of aging takes place with something we refer to as methylation, and that is the silencing of genes. As you age, genes become silenced over time, and there's sort of a general pattern of age-related silencing of genes. Cancers are helped by silencing of specific zones of genes. And that actually refers to the CPG area of the DNA, but that aside, it's unique. It's this one little spot that it preferentially methylates the genes. And it does that so that it can turn off genes that say, stop growing. It can turn off genes that say, stop trying to spread, stop invading into tissues that you're not supposed to do. And so what ends up happening is you have a methylation signature in your blood. Whereas if you have normal age-related methylation, it's going to be this general pattern. And if you have cancer-associated methylation, you'll have a normal pattern with a spike in this CPG zone. And so the methylation signature was first developed about 5 or 6 years ago as part of a large study. And then several companies have been working on it, but Grail, with huge venture funding, was able to capitalize and really develop this further. So they can look in your blood and say, this person has a methylation spike that looks like that there's an occult cancer hiding. And based upon the genes that are methylated, they can also help to say, we think that this is going to be a colon cancer, or we think that this is going to be an ovarian cancer, or we think that this is going to be a lung cancer, with about a 90% accuracy rate. So it's not perfect, but it certainly sets you off in the right direction. And so how could this impact overall outcomes from cancer? Well, I already said that if you catch pancreatic cancer at stage 1, you have surgery and you can cure it. If you have pancreatic cancer at stage 4, we have no cures for pancreatic cancer that's stage 4. So if we can catch stage 1 and pancreatic cancer more often than we catch stage 4, we are going to improve outcomes there. And so this is in its infancy. They have already done a very large study showing that they found cancer successfully. And this is a follow-up validation study of tens of thousands of patients to really get the insurance companies to be obligated to say, okay, this is the screening test the primary care doctors are going to get on their patients as part of the annual physical. So that's one piece of non-invasive blood testing to look for cancer. Another way to monitor cancer is with something we refer to as circulating tumor DNA or ctDNA. So we talked about cancers have these mutations in them that cause them to do bad things, grow where they're not supposed to, travel to places they're not supposed to go to. And the cancers will actually shed that mutant DNA into the blood, and we can now test for it. And so when we test for it, we can find, oh, look, you have a small frequency of mutation 1 in your blood. What is the next generation of that now is the company's name is Natera, and they developed originally for non-invasive fetal monitoring, looking for Down syndrome and things like that in pregnant women, looking for genes related to Down syndrome. So now in cancer, they sequence a patient's individual tumor, make a thumbprint, essentially personal identification to that person's own unique cancer, and create a series of probes to go after the mutational levels in the bloodstream of that patient. And they've shown in patients with colon cancer that after you've had surgery, if you have a positive personalized ctDNA test, you are 40 times more likely to develop relapse than if you don't, because it means that you still have microscopic cancer hiding in your body. So this is the type of thing that we can leverage to figure out who needs treatment, who doesn't need treatment. People who have immune therapy who clear their ctDNA have so far all been long-term 5-year survivors. And that is tremendous. You don't see long-term survivors in 100% of patients, but with immunotherapy and personalized ctDNA, that may be the case. And we are, yes, in conversations with the company for monitoring that in patients with lung cancer and melanoma and colon cancer. I've also got a proposal to the Melanoma Research Alliance that's under review as we speak to try to leverage that in patients with stage 3 melanoma to see if we can figure out who doesn't need as much treatment because their ctDNA is negative. So there's a lot of really neat blood tests. We have finally gotten to that point with really sophisticated non-invasive monitoring.
So can I also integrate one other to your question, Hank, which I think is really important. So prevention becomes a really important strategy. And hopefully one could prevent, if an early stage cancer is detected, its ability to spread and metastasize. And if a person has a genetic propensity to the disease, you could start that chemo prevention and therapeutic prevention early. We've started actually work with Dr. Trevino at the medical center in pancreatic cancer now. And we're finding that our small molecule that I'm working on with Andrew will work with 5-fluorouracil and gemcitabine, which are the standards of care now, and allowing them to work on human patient-derived samples. So there are ways, if you can identify it early, you can do prophylactic treatment, hopefully, in the future to prevent spread and prevent metastasis. That's our holy grail.
Dr. Fisher, I have a follow-up question. So in terms of your molecule that you're working on, will it sort of roam the body looking for metastatic cancer cells to attack them? And what will the delivery method be? Do you anticipate, will it be an infusion or an injection or pill?
That's a great point. I know I'll always get the good questions, Cindy. So the bottom line is, one of the issues, we had a first generation drug, outstanding, worked really well. But in animal models, you had to put it intraperitoneally, which is not the way you're going to deliver any drug to a human. we've now identified the next generation of this that you can actually deliver using an IV infusion. And it is working extremely well as the original one worked by injecting in the peritoneal cavity. So we're at a point now where we're progressing with this. The real critical bottleneck in all of this is toxicology, and that's the most expensive component of this. For a single drug like this, it could take anywhere between $1.5 to $2 million just to show it's safe. And and the other way we're trying to look at this: can you make an orally delivered version of this, which would be really pretty exciting at this stage. So I hope that partially answers it.
Yes, absolutely. Do we have any other questions for the audience?
Yes, I've got a question, please. This is Metastasis 101. What makes the cancer decide, I'm tired of living here, I want to go explore and find another place to live?
Clonal variability. I'm just, and then I'll let Andrew jump in. So cancers continue, unfortunately, to evolve. And you can have cancers that exist at a state where they've not spread for a long period of time. There's a concept now called cancer stem cells, which is a very small population of the cancer cells that have the ability to break through their primary location and get into the bloodstream. Many of those that do that are destroyed. They never get to a secondary site. But it's the rare ones that now are embodied with new traits. Some of those can be because genes are methylated, other genes that control this, which are suppressor genes, are shut down. And now this cancer can spread to other sites. So it's a continuing evolving process. And unfortunately, as we age, there are more and more changes that occur genomically. And this can be an issue where prevention and treating at that stage will work. But it's not as if they have a mind of their own. Andrew, you might want to integrate this, but they have some are stronger than others. This has been called fitness ability, and they can survive where the other ones cannot.
Yeah, if metastasis was an easy concept, we would have solved it by now. There are so many features, from the genes that are broken, the additional genes that accumulate, because you have cells that are deficient at repairing their errors, and they're growing too fast and they're not repairing. So over time, they collect more and more errors. And the errors that say, stay where you're supposed to stay and don't migrate to somewhere else, accumulate, and then they get to move. There are also local factors, whereas tumors get to a certain size, they start to have blood flow changes that triggers processes that causes the cells to revert to stem-like phenomenon. I mean, cells, there is a part of the body in time of development when cells are supposed to move around the body. And that is during embryogenesis and fetal development, right? You go from a cluster of cells and you have organs that are moving through the body, gonads descending from high in the chest down into the groin. Motility of cells happens, but it gets turned off when you're born. You're no longer having cheek show up on your, on your arm or lips on the top of the forehead, because those processes turn off. But when things break, cells can move again. And that's one of many of the complexities that go into why cancers can metastasize. And those that gain that function can just continue to do it and do it and do it and do it and have progeny. Over time, cancers become more aggressive because the most aggressive version takes over. You can see that with what happened with COVID. This is a biological phenomenon. You had your alpha, the original strain, and it was the dominant strain, and then Delta took over, and now there are very few cases of alpha because Delta was more contagious. It had a survival advantage because it could spread faster and to more people. So that is the same process. You can have a cancer that after a division now has a new feature that allows it to succeed better than the other cancers. And so over time, cancers become more difficult and more dangerous to treat.
And that's the key. They're not static. They keep changing. And that was my original point, that if you hit one stage they're at, there may be something that's past that stage that the molecule you're using will not work. And so we've gone after the most aggressive ones. And we've shown that even ones that are resistant to a certain therapy can be treated with the combination. And in some cases, the same molecule that didn't work now works. It's a really complex process that's a give and take and going back and forth between the lab and the clinical component. And that's why these phase 1 trials are so important, to define the population that will respond best and see if you can improve it in those that are not responding as well.
Thank you.
Well, thank you, Dr. Fisher and Dr. Poklepovik, for a fantastic conversation today. I hope that our audience enjoyed it. And we are so grateful that you are doing the work that you do and that you took time out of your busy day to be with us. And I'm going to turn it back over to Sharmika to wrap us up.
Thank you, Cindy, for helping moderate today's conversation. And thank you both to Dr. Poklepovik and Dr. Fisher for your presence here today. And thank you for joining us as Massey Club members and supporters of Massey, and for your investment in Massey Cancer Center and the research and life-saving work that we're doing. Your generous support helps arm our scientists with the resources to pursue innovation in cancer research. And I hope you found today's conversation inspiring. And as we close, please join us in spreading the message far and wide about the innovation and life-saving work happening at Massey. Also, I want to make sure that you mark your calendars and save the date for our Massey Club 30th anniversary celebration on March 29th, 2022 at the Country Club of Virginia. All of us at Massey are hopeful for a future without cancer, and we are so grateful for your investment and for your partnership. We hope you enjoyed today's presentation. Thank you so much and have a great afternoon.